We have seminars every second Wednesday of each month, except this time, because of collision with the American Geophysical Union meeting, it's the third Wednesday. But we are continuously looking for presenters from either Europe or United States or anywhere else to present in this series. And now over to Sue Ellen, who is going to introduce our today's speaker.
Yes, and today we're pleased to welcome Anthony Kirancic from Woods Hole Oceanographic Institute, who is also a lead scientist at Martha's Vineyard Coastal Observatory. He has a Bachelor of Engineering in Civil and Environmental Engineering from Vanderbilt University, Master's in Oceanography from University of Rhode Island, PhD in Physical Oceanography from Oregon State. He's an expert in coastal ocean and atmospheric circulation, the role of ocean mixing in coastal dynamics, and has developed new methods of sensing the ocean and atmosphere using both in situ and remote instruments. Right now, he serves as the non-federal lead of the U.S. Department of Energy's Offshore Wind Forecast Improvement Project 3, focused on the U.S. East Coast, and runs WHOI's Med-Ocean Reference Station. Over the past 8 years, Anthony has been working with research and industry partners to establish ocean testbeds for ocean technology adaptation and integration into the emerging U.S. offshore wind energy industry. Anthony, take it away.
Thank you. Thanks very much for having me. Thanks, Sue. I'm sorry that I must have given you a really long description to read. That wasn't certainly necessary. My apologies for that. So if I gave that to you, my apologies. I'm happy to be here. I have about 30 slides to talk about the Wind Forecast and Improvement Project 3. This is the first offshore version. I'm happy to take any questions along the way. Just shout out or say something in the chat. I'll be looking at that as well. But the goal here for me anyways is to let this audience, which is I see some folks from that I don't know and some folks from that I do know, that this might be a little bit of a refresher for understand the project, the data coming out of the project, the goals of the project, why we're doing it, where we are doing it, and then be able to understand the results that are coming down the pipeline in the next few years and work with folks that are engaged in the project overall. So what I'm going to do is kind of motivate or remotivate the Wind Forecast Improvement Project, why we're doing the field study where we are, what the field study is, what the modeling effort is, and then show you some initial results from the data sets that we've been collecting, as well as some preliminary results from some of the modeling efforts as well. So it's an overview to the entire project writ large. And I'm hoping that this audience will see lots of talks from WFIP-3 collaborators over the next couple of years as we get into the analysis phase of that. So again, I'm happy to be here. I'm excited to tell you more about this project. So the Wind Forecast Improvement Project is sponsored by the Department of Energy. Shannon Davis is our project manager. And we are focused on this region of the U.S. East Coast, which is in my backyard here, the northeast part of the Mid-Atlantic Bight. Offshore of Martha's Vineyard, the islands of Martha's Vineyard in Nantucket, which is near Massachusetts and Rhode Island in terms of the U.S. States. So there's lots of folks that I'm working with here. I've listed some of them on this this page. There's other ones that there's lots more to thank as well, and that are folks that are engaged in the project. Okay, let me, I gotta do this. Okay, so the third version of the Offshore Wind Forecast Improvement Project, this is the first one focused offshore, has 3 main project goals. The first is to understand via observations the regional meteorological and oceanographic processes that directly affect wind resource characterization. Second is to improve via modeling updates parameterizations of the boundary layers and their interactions through the wave-mediated surface. And then thirdly, to evaluate via fully coupled models and wave and wind and ocean models, turbulence parameterizations, and specifically industry applications for resource characterization. So this is where we're trying to use the observations and the modeling updates to turn those into industry products that will have a value to the wind energy industry and the science community that is looking at data sets around the wind energy industry. Okay. So the focus area for WFIP-3, which is the acronym that we call it, is the Massachusetts and Rhode Island wind energy areas. As I introduced earlier, this is the island of Martha's Vineyard and Nantucket. These are on the northeast edge of what I call the Mid-Atlantic Bight. So this is New York City. Boston is just out of the page. Virginia is below or right here. Washington, D.C. is right there. And so there's these 6 lease areas for offshore wind energy that have been let to developers. 2 or 3 actually are in active stages of construction. Vineyard Wind 1, which is pictured here in this purple box, and then 2 Orsted areas, one being South Fork, and right now I forget the name of these lease areas because there's lots of them. So there's wind turbines in all of this boat-shaped pattern as well. So these are areas of active development, and the hope is to also understand the wind resource a little better to improve models for this. So again, the focus area is on this northern component of the Mid-Atlantic Bight where there's active development in the U.S. Okay, so at WHOI, my institution, we've been working in this area for a long time. This has been my backyard for research for the past decade. I am a coastal oceanographer by training. I do run our air-sea interaction tower, which is pictured here from the water side, where we've been taking observations via a fixed cabled observatory since 2001. As Sue Ellen said, there's been a public data repository of industry-validated LiDAR observations of hub height winds from this air-sea interaction tower since 2016. So this is a tremendously long record now of hub height wind data collected in the area. This is about 12 to 13 nautical miles north of the wind farm lease areas. We've been collecting data for a long time there. You can go find those observations at one of these 3 links right here. So we know a lot about the area and the background of it. The northeast shelf of the U.S. here is an interesting place for wind conditions and oceanographic conditions. I'm going to introduce a little bit about that to set the stage for you. Here's some wind distributions or wind roses. So in the summertime, we have winds generally from the southwest. And so there's a long open fetch for the winds that are approaching the area. And in winter, it's different. The winds are generally from the northwest, so winds are coming off of land to the ocean. We have, obviously, for fetch in the ocean, it's a bit more limited. But one of the things I want to focus on or leave you with for the U.S. East Coast, in this area of the East Coast compared to, say, the West Coast of the U.S., is that we have generally winds out of the southwest in the summer, winds out of the northwest into winter, but they're highly variable in time. So winds are not constant for days on end like they might be on the Central California coast. We have a strong synoptic scale variability of wind directions and fronts moving through. So turbulent kinetic energy mirrors some of those observations of the wind direction and speed in summer because winds are coming off the ocean with a very long fetch. We have very low TKE. And these are based on observations that were both from point sensors and LiDAR extractions that Nikolai Bodini and I and Julie Lundquist did a few years ago from the LiDAR observations. Wintertime winds have higher TKE for lots of different reasons. First and foremost, that the system or the winds are coming from land into the ocean. So there's a stronger seasonal cycle of hub height turbulence there. The ocean underneath the atmosphere is also interesting and variable. I'm an oceanographer, so I'm always going to say the ocean is interesting. This is a figure that shows the color is sea surface temperature measured in August of 2019. The arrows on the page are observations of currents at the ocean's surface made from coastal radar systems. These are land-based antennas that I personally run. They are on all the islands and at all the sites that the WFIP-3 operations will take place, you'll see later. And what we're doing is we're measuring the surface top meter of the ocean spatially, and we're getting vector velocities from that. And so you can see from this snapshot in time, this is a half-an-hour average, and then a co-located SST snapshot, that there's a lot of eddy activity, a lot of fronts and squirts and jets in the ocean that have the potential to impact the atmosphere above it, either via differential heat transfer. There's a 10°C temperature change across these very small frontal regions, or the ocean currents at the bottom of the atmosphere. So it's an interesting place for the ocean and the atmosphere to measure. So the team of the Wind Forecast Improvement Project is big. This is a big effort, and there's a lot of folks working on this. I lead the non-federal team of universities and other. We have some consultants, and this has not been updated. I just realized in a little bit, so I need to change some of the logos here. We have a whole cadre of national labs of the Department of Energy that are working with us from the Pacific Northwest National Lab, Lawrence Livermore, NREL, and Argonne. And then the third leg of the observational modeling stool is a whole team from the NOAA labs from the NOAA Weather Service, including the Global Research Lab, the Physical Systems Lab, and the Global Monitoring Lab. And lots of these folks are based in Colorado and are experts in measuring parts of the atmosphere that we obviously at WFIP don't measure. And it's a great collaboration of this kind of, I like to think of this as a three-legged stool between the three groups of folks that are working on the project. I do have a fourth column here. And so that fourth leg, I guess, would be, we have a really strong user advisory board with developers that are working in the region, folks that are key stakeholders in the area, like our local grid operator, which is ISO New England, and then the U.S. Coast Guard, which is in charge of search and rescue and also certifying vessels for operations in the wind farms and in the U.S. EEZ. So a lot of effort on all sides here, from the research, the development, as also this advisory board, to make sure that the results that we're hoping to get will be timely and informative and useful for the industry. So the approach that the full team is taking has this kind of mirrors that four-leg process, but a little bit different here in what we're looking at. From the parameterization development, or the development of parameterizations, the simulation of data, running three-way coupled models between the atmosphere and the ocean and surface gravity waves on the ocean surface, and then the observational assets that different teams are all contributing to. And you can see how those teams are overlapping and interacting here. The full goal of all this effort is to improve the operational weather forecast. And so we want to collect data, make new parameterizations, and test those in operational weather models so that we can make those models better. And if we make the operational weather models better, then all the other value-added products that stand on top of those will improve by default. So in terms of a timeline of this project, the award to WFIP leading the non-federal team is 5 years long. We're actually just starting year 4 of our efforts, so closing out 2024, and we're most of the way through the observations. That's exciting for us because we've collected a lot of data so far, and we're excited to see the analysis happen. And so what I'm going to be telling you about is a lot of the observations that we have collected so far, what's kind of left to be done, and some preliminary results of what we've seen here. Okay, so the observations that came in WFIP-3, the inset here is, again, the Atlantic coast, or the mid-Atlantic bight of the U.S. All those blue dots are National Data Buoy Center buoys that are measuring standard surface meteorology. And then I have this inset box, which is blown out here to the lease areas that you saw previously. I'm here in Woods Hole. New Bedford, which is kind of a marine commerce terminal now for the offshore wind industry, is located right here. And then you have the islands of Martha's Vineyard, Nantucket, and this little guy over here is Block Island. So you see the lease areas, you see all these dots on the map that are the small dots, which are the remote sensing from the radar systems I mentioned earlier, as well as these bigger ones, which are in situ assets or on-land assets. And I want to walk through all those things so you guys kind of realize what we're doing. So there's 6 land-based stations. Those are all marked in red here. And there's a whole host of instrumentation that we have on there. Everything you'd want to have to measure the bottom part of the atmosphere are there, between profiling, scanning lidars, thermodynamic profilers, etc. We have 6, actually 5 deployed mid-ocean reference buoys. I'm going to call these sentinel buoys, and that's these magenta lines here. And they are measuring the surface fluxes that you'll see. We have a number of profiling lidar buoys, some process study sites, both the Air Senior Action Tower that I mentioned earlier, and then this large barge that I'll talk about later on. We're also doing atmospheric soundings during key events from Woods Hole, right off our dock. And then along this transect line, which via a shared project, there's another project funded by the National Science Foundation where we're tagging along on the vessel with them as they steam out and make stations at all these little dots along that line, and we're launching balloons at the same time so that we can capture the atmospheric availability at these two sites via this transect, and that's happening quarterly or better. And then the remote sensing I talked a little bit about. Okay, so observations on the land-based sites. This is a picture of our site at Nantucket. It's a nice location right on the south coast of the island. This is kind of a small segment of the instruments that are set up there. Again, anything that you want to put to measure the bottom part of the atmosphere, from scanning lidars, celiometers, total sky imagers, radiation tables. Behind out of view of this picture are a whole host of a W-band radar and thermodynamic profilers and a small MET tower that are measuring the surface ocean or the surface atmosphere and the area remote sensing above it at that location. And so each of these red dots has almost the same setup of this whole suite of instrumentation to measure the atmosphere above the land near the ocean at all these locations. And so they're kind of surrounding the lease areas to the north. We also have a site out here at the outer part of Cape Cod, which is doing the same and providing kind of data that's a little bit farther afield for certain weather conditions like nor'easters that would have winds coming from the northeast. So all these sites have about an 18-month observational period. We're about a year through that, so we have about 6 or 7 months to go for these sites. In the water offshore, both my institution, Woods Hole Oceanographic, and the Pacific Northwest National Lab have put buoys in the water from the LiDAR buoys that the Department of Energy has been funding PNNL to do. There's one out right now. There'll be another one out soon. These buoys right here are the smaller ones, which I'm going to call flex buoys, or they're named Sentinel buoys. I'll talk a little bit more about what's on that buoy on the next page. And those are deployed at all these kind of magenta dots through the site. And then we at WFIP also built a LiDAR buoy specific for this project as kind of a one-off. It has a ZX marine profiler on the top of it, and it's solar powered completely. So it's running here downstream in the summer winds from the central barge site between there and Nantucket. Okay, so there's the LiDAR buoy, there's a flux buoys. The flux buoys I want to focus in on a little bit more detail so you see what is on these buoy systems, because it is, I think, interesting and useful for the folks that are working in the energy space to understand how the measurements needed to get good fluxes between the ocean and the atmosphere over the ocean. So the flux buoys, or these Sentinel buoys, have a number of sensors. There's about 3 different ways they measure wind. From an RM Young wind monitor, a GIL 3-axis sonic anemometer, and then a Vaisala WTX like weather system. Obviously, the main one is this 3-axis sonic anemometer, and these other 2 are more or less backup for wind speed and direction. There's a rain gauge. We have air temperature, humidity. There also is if you go over to the other side of the buoy, we have solar radiation sensors and infrared radiation. There is a dual GPS IMU, so that this system, the buoy is moving around, but between the IMU and the 3-axis sonic anemometer, we can do momentum fluxes that have removed the sources of motion from the buoy movement on that anemometer to get the momentum flux and the heat flux between the ocean and the atmosphere at this level. And this is about 2 meters above mean sea level for the measurement. Okay, so that's what the flux buoys are doing. Here is a couple of data sets or some looks at that data from the past couple of months. This was the end of September, beginning of October, and we had a couple of big storms happened at this period with, right at the end, sort of September 23rd-ish, we had winds up to 15 meters per second. There were some nice significant waves up to 3 meters a second here. The buoys also measure significant wave height and directional wave spectra on the buoy. And then here's the LiDAR wind speed from that one day, more or less, of this big peak winds. And so some really nice observations to take a bigger look at as we move forward. And so here's an example just of what those systems are measuring. Okay, so I wanted to come back to this plot because like I said, the LiDAR buoys, the flux buoys are numerous and kind of surrounding the lease area. We have our air senior action tower in the middle of the northern part here. This is a picture of it again, showing the array that's on it right now to capture the same type of momentum fluxes that the buoys were capturing between the atmosphere and the ocean below it, but at different levels above the ocean. So the very top of this tower goes up to 26 meters above mean sea level. And then below that, at about 5 different places, we have sonic anemometers and different types of pressure sensors or humidity sensors or liquors to measure the turbulent momentum flux at different levels. So what's the vertical profile or the flux divergence through the bottom part of the atmosphere here? And also what is the moisture flux and the heat flux that's happening right above the atmosphere. And so this system was set up last November. It's been running for about a year or more, and it'll continue to run to the summer. So a really long record of detailed estimates of momentum fluxes through the bottom 26 meters of the water column at the air reaction tower. And again, during summer conditions, the winds are out of the southwest. And so even though this tower is 2 nautical miles off land, you can see Martha's Vineyard in the background, you are getting open ocean conditions that you're seeing at that site. So the third or the fourth, I guess, aspect of the at-sea operations is this anchored barge. And we've put a lot of effort into that this past summer. And so I wanted to talk about the barge for a little bit. So this is a video that's going to play, and I'm going to talk over it. So the purpose of the barge is to take all the instruments that we would have on the land-based sites and all the flex measurements that we would like to make on the offshore tower and put them offshore in the lease areas for as long as possible, and to make measurements for as long as possible, as robust as possible. And so there's a whole bunch of limiting factors here on power and communications and sensor maintenance. And the barge was set up to try to minimize that. And so it's a pretty big anchor system for the barge because the waves do get pretty big. It is about 150 feet long and about 54 feet wide. There's a whole host of systems on the barge. There were on the barge to maintain the anchor there, but we also have this 26-meter mast matching what was present at the air reaction tower. It's powered by solar panels as well as a battery bank as well as backup generators. And then on the aft in the middle of the barge, you see these 2 containers that host all those sensors that would have otherwise been at a land site. And so I think we're going to stop here and show the reason we did a barge here is that we have low flow distortion over the bow of the barge. So you can get a lot of different flux measurements at different heights, just like we could on the other tower. But then all these other sensors from sonic anemometers, scanning lidars, microwave radiometers, thermodynamic profilers, W-band radars, celiometers, profiling systems, and we also had a host of bird and bat sensors because there were other DOE projects happening at the same time that were focused on the wildlife and wildlife issues, not just the physical environment issues. So again, the purpose of the barge was to do all the measurements that we would make on land or at the tower and do it offshore in the middle of the lease areas. So the barge did 3 separate deployments over the course of this past summer. It has spent, and the 3 separate deployments were due to weather. It's a flat plate in the open ocean. You can't leave it out there in all types of wave conditions. But we did a total of 85 days on station. And so again, this is unmanned. No one was aboard when it was out there. The longest deployment was about 40 days straight with no one actually touching it. And so the power system was pretty, I think we did a pretty good job with the power system. It was a system of systems that we put together here at WFIP, and we turned it on in the middle of May, and we turned it off in October, and it ran for over 130 days straight with nobody touching it. So that was a good achievement for us and able to power all these sensors. Just for reference, the sensors that we had on the barge were about 7 kilowatts continuous, which is way more than a normal house takes. And so we were out there powering a house for the bulk of the summer. We had real-time communications and data delivery via satellite. Here are some real-time images from the barge when it was deployed this past summer. And so we were getting this data in real time from cameras mounted on the mast or even at the stern here looking forward, so you can kind of see what was happening. And then we had this data that was actually coming off in real time from the top of the mast that was telling us the heading, pitch, and roll, and heading, pitch, and roll and kind of their standard deviation errors. And so if something were to happen, we would kind of see that. We did have the barge was meant to be deployed during summer because wave conditions are a little bit less in summer. We couldn't have done this in winter, but we did leave it out there in sea states up to about 4 meters significant wave height. And we did have communications with it from a couple of different backup positions, including satellite AIS systems. And so this is a screenshot from marinetraffic.com. For those of you that work out in the ocean frequently, you might use this as a website to see where vessels are. And so here's our marker sitting there for folks to see to make sure that it doesn't get hit or something like that, and all the other vessel operations that were happening at the same time. We had that positional awareness. The barge was out in generally small conditions because of the nature of the system, but we did have some more significant storms. Here's some screenshots from those camera systems. You can see that when the waves were hitting from the beam or the side, we did have some roll that was getting water on top of the deck of the barge and sloshing around. And so it was out in some more significant conditions, but it was a useful platform to utilize for this. And so I think it was a highly successful. All these sensors worked almost all the time. So with the rest of the time I have here, I kind of want to go through some preliminary results. Like I said earlier, we're still in the observational phase. The barge component of the project is done. We had a NOAA ship that was out for the same purpose with the same sensors at the same location as the barge. It was out this past last couple of weeks. It had some significant weather, so it had some short deployments out there on the barge to both launch balloons and then have those same sensors from the barge out there to record vertical profiles of the thermodynamic properties as well as the wind and other properties, cloud layers and stuff above the site. But what I want to talk about are some of the individual results that have come in so far, and just to kind of give you an idea of the types of data that we'll be able to talk more about in the coming years. And so the first one is the impact of waves on stresses in the ocean. So here's again a picture of the air interaction tower. I'm going to point out that the mast going down from that mezzanine deck, or the diving board we called it, is bent over. This was actually due to storm damage that happened in December of 2023 and again in January, and I'll talk about that at the end. But I want to point out that this mezzanine deck is 12 meters above mean sea level, and so this strut that extended down about 4 meters from that got hit by waves during that storm. So it was a really big storm. So but Seth Zippel, who's now at the Oregon State University, has been spearheading the observations from the tower of turbulence, and has been looking at how wind and wave conditions occur, if are there equilibrium conditions or non-equilibrium conditions, how often those occur, and then how much of the energy is going down from the atmosphere to the ocean and how much is it going up from the ocean to the atmosphere. If the waves are moving faster than the winds, the waves can actually push energy up into the atmosphere, and that's something that Seth's been interested in with his research. And so the important point for that is that the wave energy can alter wind profilers during weaker ramp events. So if you have times when the winds are weak, you actually have a feedback between the wave field that might be not in equilibrium with the winds, transferring energy back to the atmosphere. And that's pretty interesting. Here's a plot of the type of calculation that Seth's making using the turbulence sensors on the tower. So this is the total cross-spectral power from the I'm sorry, let me go back here a little bit, from the horizontal in downwind or upwind and the vertical velocity. And you can see a total, and then there's a part that's coherent with the waves. And that's what's being driven by the waves pushing back up again. And we have this pressure slope term that's actually also feeding into the offset in the phasing between the waves and the wind. And that's allowing the waves to impart energy back to the wind field. And that's something he's been interested in again. And that's more of a weak wind conditions. He did actually have other measurements. Like I said, there were these bigger storms in strong wave or wind conditions. So here's a couple of spots where the winds were over 20 meters per second. These aren't tropical storms like cyclones or hurricanes, but they are kind of bigger winter storms where we have them more frequently. that can get winds up to 20 to 25 meters. And that's just at 26 meters above hub height. Obviously, at the 26 meters above mean sea level at hub height, that can be stronger. The second part from Seth that I wanted to show you really briefly is the vertical momentum flux estimates from the offshore tower that was on the barge. And so again, Seth measured momentum fluxes or potentially momentum fluxes at 5 different locations on that 26-meter tower to look at the vertical structure of those fluxes. And here is kind of the time series of wind speed. And here's you see example of when the barge was in port and then in the ocean. So there's the shaded areas are in port, the white areas are when they're in the ocean. And you see a significant difference between the wind speed and the momentum flux. So this is U prime, W prime, and then the heat flux when we're in port versus in the ocean, right? So there's a huge land-sea difference between in port and the ocean. There's a significant summer and fall difference that you can see between the deployments that were in July and even in June, and one that was August to the end through the end of September. And then you have these significant storm conditions where, again, a lot of these are profiles of 6 or so different 5 or so different locations, and you can see kind of the downwind flux that varies vertically just across a pretty short area here. And so these are corrected for the small motion of the barge that did exist, which was obviously better than a buoy system would have done. Moving on to preliminary results, some of the model analyses, I want to focus a little bit on the event log. And Nicola Bodini from NREL has been leading this for the project, although there's been a whole host of folks across both the non-federal side, the DOE lab side, and the NOAA labs that have contributed to this. The event log, just like WFIP-2, has done daily logging of weather conditions in the region. They've logged what weather conditions were happening, how did the NOAA models or the HER model perform from its forecast, and then were there wind energy related processes like low-level jets or lulls or ramps that we as a group should be focused on or come back to look at to see how well the models perform, how well the parameterizations perform, and how we can make things forecast and do better. So as an example of kind of some of the statistics that Nicola and the team have been able to collect so far, there's been about 100 days or more between this year, from February when they started to November, when I think he gave me these statistics, that had low-level jets in them. These are small scale structures in the wind field at hub height that have the potential to provide wind shear and veer across the rotor plane. These are things of interest to the energy industry. 40 plus days of high relevance for model development. Those are kind of the lulls or the ramp events that would be interesting just to make sure that the model is getting what's happening correct. And then here is an example of one of the websites that the PSL team, the Physical Systems Lab at NOAA, has been running on behalf of the project here to compare some of the observations that we're collecting using the thermodynamic profiler on the left, and then some of the radar wind profilers or the WMN radars on the right with the HER model output at that location. And so we can make these one-to-one apples to apples comparison on even a daily basis to be able to fill out the event log with how the observations are doing and then be able to come back later on to do that. So if you have more questions about the event log, Nicola Bodini is the person to ask about that. Also at NREL, Stefano has been working on thermodynamic profiling. There's a nice group of folks here at WFIP-3 that have been using assist type infrared spectrometers to provide the downwelling spectral irradiance, and then into a Tropo-E algorithm that one of our team leads from NOAA, Dave Turner, has perfected through a number of years here to estimate profiles of the temperature and humidity across the boundary layer and above. And so here's some examples from a profile at Rhode Island. So this is taken at this site right here on mainland Rhode Island over the course of about a day in the bottom 2 kilometers of the atmosphere, remote sensed humidity and temperature via this extraction system. It's a really interesting way to do it. I think it's an exciting data set that they're collecting at all of these locations, not only Block Island, Nantucket, Rhode Island. It was on the barge, as well as there was one on Martha's Vineyard that's not marked here right now. So again, these are able to characterize spatial variability of temperature and moisture in the bottom part of the atmosphere, and then look at the atmospheric stability and boundary layer height. So that's pretty exciting, and I think they'll be a great data set to help us carry out our project goals. Moving into modeling, I wanted to highlight a little bit briefly the work that Branko Kosovic, who's now at Johns Hopkins. This is the algorithm, one of the emblems that wasn't on the first slide there, has done on understanding the impact of different parameterizations on hub height winds. And so Branko's been running some nested model simulations of cold air outbreaks. And so here's kind of an example of a satellite image of the cold air outbreak that he's been trying to model in the preliminary work as the rest of us are collecting observations. And then here's some examples of the hub height winds using one-dimensional MYJ parameterization for the planetary boundary layer. And then here's the 3D PBL scheme that he's been working on, the same picture at the same time. And then you have the difference between those two models, which is related to the difference between these parameterization schemes. And so as Branko's shown here, and he has had a couple talks recently about the details of this, there's some key differences between the one-dimensional and the 3D PBL parameterizations. And it seems like for cold air, polar air over a warmer ocean, there's some mesoscale convective circulations that aren't as well resolved in the 1D, and the 3D PBL might be doing a better job. And he actually was comparing in the talk that he gave last week at the fall meeting, this data to some data that we had collected at the ACIT to validate the effectiveness of the 3D PBL. So at hub height, it seems like the difference in mesoscale convective structures might have some impact on hub height winds and the turbulence intensities. And so I'm excited to see where this work goes over the latter half of the project here. Okay, so I'm going to end my last preliminary results with some work that I've been doing. I'm really excited about this. Again, I'm an oceanographer. I measure the coastal ocean via remote sensing and in situ sensing. One of the tools I use are these land-based radar systems. These are antennas on the beach that look out. Here's a plot of where they're measuring surface currents via sites that are at the same sites as the WFIP-3 sites that I've shown earlier. This plot on the right is surface currents. So these are kind of streak lines of a little bit of particle trajectory from the frozen flow field. So this is just a half an hour of data with convected a little bit over time just to give you that sense of motion. And the point here in saying is the ocean is highly nonlinear. There's lots of small scale eddies and streaks are going on. And so the land-based high frequency radars are providing vector surface currents below the atmosphere in the WFIP-3 area that can aid and model systems that are looking at coupled winds and waves and ocean models below. But one of the products we're also looking at that I'm excited about is we're looking into algorithms to use those same radar extractions or backscatters to measure spatially distributed surface winds from these land-based instruments. And so these are, again, we're measuring waves at the ocean's surface that are very short, just like satellite scatterometers do. The difference between the land-based radars and the satellite products is that we're there all the time measuring. And so here's a kind of a validation plot here of the buoy winds that's located at this center site here that are black. My estimate from the radar systems are in blue, and then the ASCAT METOP-A scatterometry products, when they're available, are shown as those dashes. And so there's some real usefulness potentially for this data set for folks looking at surface winds and the scales of surface winds over the ocean in the coastal ocean because of the high spatial, kilometer scale and high temporal, it's half hour or better repeat rate of the radar systems in measuring, the land-based radar systems in measuring surface winds, as well as using satellite products. And so here's kind of an example of the combined wind vectors for one of these time periods from that. So this is a look at the preliminary results. I don't want to go too far over time here. We did have some significant storm impacts early on in the field study. I mentioned that earlier when I was showing you the tower spar that was bent. Our site along the south coast of Martha's Vineyard got inundated with waves and sand early on in the period. This is after a storm that was December 18th. Here are some nice scanning LiDAR systems that were up on stands that used to be behind the dune, away from the surf zone, and became in the surf zone with sand all around them due to these storms. And so this building and all this stuff has been since removed because of the storm damage. And here's a picture that one of the local Martha's Vineyard person took of the waves kind of coming through the whole array at that time. So a bit of storm damage that's been complicated in the measurements, but we've been able to shift around. And I think these observations, these instruments are now on Nantucket doing some really nice winter work of small scale structures over the inner part of the ocean. Okay, so the last slide I have here is for additional resources. If you want to know more about the overarching team, the experimental plan or field observations, there's a website here that we at WHOI are maintaining. All the project data for WFIP-3 will be hosted with all the other project data for the Department of Energy efforts, which is at this A2E energy repository. WFIP-3 is the project to search for, but I will say that at this point, at this time, there's an embargo on data in place until about mid-2025. This is not my, this is a project-wide doing, and the goal here is to give folks that are collecting the data observations to get the best data product possibly uploaded into the archive before things are released for general public use. We have gotten a lot of interest in the data sets that we're collecting, and we're certainly excited to release everything into the public space because I think it'll be useful for folks to look at, but we just need a bit more time to make sure that we're giving the public the best data set possible. So I think that's the last slide I have. I'll end here and I'm happy to take any questions.
Thank you very much, Anthony.
Yeah, virtual applause. Thanks so much, Anthony, for this wonderful seminar. Look, we're ready to take questions. Those of you who have questions, please raise your hand under the react symbol and unmute and ask your question.
So maybe I could start. Where do you think this project will have the strongest impact on the industry putting up turbines in the area? Where do you reduce the uncertainties the most, or are there any surprises that they have to take care of? Or
where do I think the industry will benefit most from the data or the modeling efforts collected from this project, right? I'm going to answer that in a couple ways, I guess. I think, you know, the overarching goal of the project is to make the baseline weather forecast better. And so if you have a better idea of what the weather will be or is likely to be, then your estimate of the resource characterization is likely to be better if that's what you're doing. For operations and maintenance, I think that is a significant issue. Certainly we're seeing when we deploy things, you know, the wave forecasts are just not right, you know, and so they're off for lots of different reasons. And that's, you know, folks are making real decisions with dollar values to them on that. And you know, obviously members of the industry have to hedge that risk in terms of how they write contracts. And so if your goal at the end of the day is to bring the cost of energy down, everything you do to reduce the uncertainty and the error in operations or other systems, you know, are going to be beneficial to that, right? So we're collecting a lot of data that folks can use for extended resource characterization. That's going to benefit folks because they can make better, more competitive estimates for power purchase agreements in the U.S. We're collecting a lot of data on conditions for folks to make sure that their O&M ideas or the pillars by which they're going to cost their O&M are reasonable, right? And then just by making the baseline weather forecast better, everything else that stands on top of it, whether it's someone who's guiding O&M operations, whether it's you know, the ISO's 3-day outlook for how much power they're going to make, you know, energy trading, all that stuff is going to improve too. That's the intent.
thank you very much. And then we have the Jiwen Fan.
Hi.
Hi.
Hi, yeah, I'm Jiwen Fan from Oregon National Laboratory. Thank you for the really nice overview for the project. I understand that the project focus more on the LC, your interactions and turbulence, but I'm wondering if there's any good data sets for the cloud, precipitation, and lightning, because those are also very relevant to the offshore wind applications. particularly lightning data.
Yeah, you're absolutely right. And I did a poor job of describing the cloud and lightning observations that we've been making. So my apologies to that, and my apologies to folks here from the project team that have more knowledge than I do. All of the land-based sites have celiometers that are measuring cloud conditions. Obviously, the W-band radars that are at some of these sites can provide some valuable estimates of clouds. In fact, we have a whole precipitation and clouds team that's led by Tim Myers at NOAA, one of the NOAA labs, that are working on exactly those types of issues that you described, both how are the clouds, impacting the operations potentially, or what the, resource characterization might lead you to, like the wind as fuel, but also how well are they represented in the foundational weather models that everything else will stand on top of. So there is a whole clouds team. I have not done a lot. I didn't do them justice here in giving the preliminary results, and so my apologies for that. For lightning, we also have a number of lightning sensors that are installed throughout the domain. We had one on the barge during its deployment period. I think it probably went through pretty fast in the video, the lightning sensor. And there's some folks at PNNL that are really interested in kind of cataloging lightning occurrences, matching that up with some of the large-scale satellite-based lightning products that are potentially available, and understanding the implications for both predictions of those conditions, as well as conditions impacts on maintenance and O&M type concerns for industry. So I didn't talk at all about that. I'm sorry, but there is a lot of work doing, and I'm hoping that in the next year or so you'll see some of those results come out. So it is there. And if you want me to put you in touch with Tim, I'm happy to do that.
Yeah, that would be great if you have the contact information. Yeah, I'm really interested in those kind of data. Thank you.
Great. I'll just put my email in the chat here, and so then you can just email me if that's okay, and then I'll forward you on to Tim or in the lightning team here.
Okay, thank you.
Do you want me to do the question in the chat? Should I just go ahead with that?
Sure. That's from Anna Maria Mariotti. How transferable were the results from this region to other regions to general model forecast improvement?
It's a great question. I'm going to first say I'm an oceanographer. I'm not an atmospheric modeler, right? So couch whatever I say with that part. I think that the region that we're sampling on the U.S. East Coast is representative of the areas in the Mid-Atlantic Bight that are slated for energy installations from Cape Hatteras to Cape Cod. I think we have some value in terms of getting more, both from a resource characterization perspective. We're collecting a lot of data. Can those data be transferable? I think the model improvements, if you're running, if you're showing that 3D PBL works really well in a couple of different environments, and then the folks at NOAA or whoever are putting into their foundational model, assuming that's going to be something that's a more globally relevant upgrade. But I guess I would say that I think understanding the role of the ocean underneath the atmosphere in these offshore wind energy areas is important and useful for the work that offshore wind energy developers and the industry needs to do. Not just the waves on the surface of the ocean, but the transfers of heat back and forth. You're putting heat from the ocean or the atmosphere into the ocean, or vice versa. How is that going to impact like the wake effects or things like that? Those are important questions that are going to have global relevance. Good question, though.
And also from Mohammed Zaranian, thanks for the presentation. Do you study underwater currents in the project as well, or any plan to include in future plans, since it might be important for support system of offshore wind turbines underwater?
Yeah, great question. The observations I showed you were of surface currents, and it was a spatial map of surface currents. We obviously don't have the same type of observational ability for currents under the ocean. At a couple of the Sentinel buoy locations, we do have current meters that are looking downwards and getting the velocity structure of the currents in the ocean. We also have a good estimate of the tides. If you are thinking about what are the biggest types of forces that a structure is going to see maybe in the ocean. The tides in this area are fairly strong, and and they're also spatially variable. So a lot of those surface measurements and the near surface measurements that we're taking will be useful for that sense for getting the tidal velocities, because those are going to be pretty significant. But we do have a couple of locations where we're looking downwards to get sort of more the near bottom currents and understanding what that drag on the bottom might be. I couldn't talk about everything, so my apologies.
And Anthony, what are you seeing in your data that maybe would be considered surprising to industry? I mean, the impact of waves on wind may not be surprising to those of us in research, but does industry appreciate some of these things?
I think that via the interactions we've had with our user advisory board, the industry is appreciative of the fact that we're out there taking data that maybe they can use later on, right? Public data they're certainly going to appreciate that, right? But I think some of the value-added products that folks have looked at for, like I said, I'm going to go back to improving the underlying forecast is going to improve all those value-added products that are on top of that. If you're an industry consultant and you're using some sort of machine learning technique that stands on top of the NOAA or the ECMWF forecast, and those things improve, your work is going to be easier to get a better forecast. I think that's one thing that's useful. I think also categorizing how often the forecasts are missing and hitting is something that will provide some value to them from the energy perspective of what does the grid operator need to think about for energy load balancing as you're getting a lot of these systems coming online. I think that's going to be something that's interesting to the industry as well. So basic resource characterization, the data we're collecting is super useful for them. They're excited to see where some of the wake studies will go. We have been collecting a lot of data in areas where there are wind turbines spinning. Those turbines have wakes. They're interested to see how long those wakes happen, or the characteristics of the wakes, sorry, and if there's data that can be used to inform future modeling efforts of the wakes themselves and what that would look like. And so I think there's a lot of uncertainty there that industry would like to get some value out of. So I think there's a couple of key areas and then some kind of second tier that folks are really excited about looking at both the data set and the results from the modeling efforts that'll come out of it.
Mm-hmm. I think it was Robert Hedland now.
Yeah, hi, Anthony.
Hi, Rob.
Nice to see you. So I had a question related to what you were just talking about in terms of when you say you want to improve this might not be your question, so I'll pose this to the field. Okay. When you say you want to improve the forecasts, what kind of scales do you think you can get to? Like the figure you showed from Bronco, like a lot of those small scale features associated with the turbulence. Obviously, no model is going to predict those exactly. They might predict the presence of them or the magnitude of the variance, but not the details. So that's maybe what's kind of the limit on the scale of improvement in terms of spatial scales, and what can the measurement array measure that could be used to help with that?
Yeah, there's a couple things there. First, you're right. This is not my general field, as I'm an oceanographer, but the parallel to the work that I do in the ocean is the idea that I measure the statistics of horizontal stirring using the radar systems, and I don't expect numerical models like yours to get the actual eddies right, but you should get the statistics right. And that right there is an order one check of how we are doing. Right. And so what can the observations do to help check if those statistics are getting done well? The point measurements that we're making, or those vertical profiles through the atmosphere, provide a lot of different data points to make sure that the models are working for the smaller scale statistics, the spatial structure across the array. The moorings are spaced out by about 20 nautical miles. So we're not getting the sub-mesoscale in the atmosphere, or maybe that's sub-mesoscale in the atmosphere. But you'll see the regional characterization of these things. I think getting fronts and small scale structures or ephemeral events as they're propagating through correct is useful for the prediction of energy coming off of a wind farm, right? And so the timing of these events is something useful to do. How far can you improve the NOAA model or the ECMWF model? That's not a question for me. That's for the NOAA guys. And I think maybe the ECMWF guys. But the one thing that I would say is, it's an iterative process, right? Like, we're collecting data. There's parameterizations that folks like Bronco are doing. Those get tested in offline models, and then they get brought online very slowly and in a concerted, like, structural way into the forecast system. So it's not an overnight effort here. And it is important to realize that there's a time scale for that kind of improvement. But those are the reasons why we're collecting the data.
Mhm.
Hopefully I
And-
answered your question.
Yeah.
Awesome. Yeah.
Okay.
I
Thumbs
would have
up.
said something similar, I think.
Sweet.
Elliot Kwan asks, who's doing the data collection and analysis for the wildlife monitoring effort? And what are the next steps planned for that research area?
Thanks for the question. Again, I'm a physical oceanographer. I don't know anything about birds and bats and whatevers. But I will say that there are a couple of projects that are funded by the Department of Energy's Wind Energy Technology Office. One is called WOW, which is Wildlife and Offshore Wind. It's being led by Duke University. I would direct you to those folks to understand who are the kind of the team of folks that are looking at wildlife observations and in the lease areas, around the lease areas, and who's kind of looking at that. I think that you probably might know that a lot of the wildlife issues are I guess not just permitting issues, but like stakeholder issues, right? Where we want to do these things to extract energy in the ocean. That's the goal of a wind turbine, right? To do this, but you want to do it without making making negatives that are worse than the positive, right? And so these are the things that folks like the WOW project are looking at. So I think it's wildlife and offshore wind is one program. There's a group of folks that is the RWSC, which is the Regional Wildlife Science. C, I forget what the C stands for. But there's a couple of organizations that have spun up to kind of coordinate and collaborate on larger scale, kind of regional scale wildlife issues that span outside one lease area and outside one state in the US and outside kind of one government agency's jurisdiction. I would start there.
Okay, well, this has been a great seminar. Thanks for all the participation and great questions. Thank Anthony once again. Next seminar is going to be on January 8th. If we have any volunteers who have something they'd love to share with the audience, please let either Jakob or myself know. And, we have various openings in the spring. So looking forward to some next seminars. And thank you, Anthony, and everyone.
Bye-bye. Thank you very much.
Thanks.
Thanks all.